So here in this lecture, we are talking about the Riemann method. So for that, let us consider L of u. We have this notation we are following, L of square bracket, which we define as uxy plus a of xy ux plus b of xy uy plus c of xy u is equal to f of xy. We call it this equation as 1, where this a, b, c and f are continuously differentiable function. With respect to x and y. And this is a linear, this equation is a linear second order hyperbolic equation, which is into its canonical form. So it is a second order. This is a linear second order hyperbolic equation which is in the canonical form. When we can say that any equation is hyperbolic? Yes, when s square minus 4rt will be greater than 0. That is the equation which we have. It is of the form r uxx plus s uxy plus t ux uyy plus some function of u ux uy x and y equal to 0. If the equation is of this type, then when r square minus 4rt is greater than 0, then we can say that it is of hyperbolic type. And the canonical form of the hyperbolic type is del square u by del psi del eta is equal to some function of phi, which is a function of xi eta u xi u eta. So that is the things which we already discussed when we are discussing a categorize or classification of second order partial differential equation. So here this equation which we have, that is this, which is of hyperbolic type, because you can see that it is of the form uxy is equal to some function of u, ux, uy, x and y, and which is already in the canonical form. And the one type of this equation we already discussed regarding the wave equation is the example of such equation. Okay, the wave equation is an example of a hyperbolic type equation. So the characteristic of this equation is x is constant and y is constant. So x and y are the constants, are the characteristics of this equation. Now let us take one function v, which is a function of having continuous second order partial derivatives. Okay, so I am considering one function, let v of xy be a function having continuous second order partial derivative, then we can talk about this. What is v into uxy minus u into vxy? See, this quantity we'll write down as this manner. That is, so I'll start with this side, not this one, but I'll start with this side. V ux of y means a partial derivative of this with respect to y minus u vy x means what? This will be gives me del by del y of v ux minus del by del x of u vy, and by product rule we can say that this is u as it is, a derivative of ux is uxy plus ux as it is, a derivative of v, it is vy. Then here it is minus sign. Same thing we can do here, that is a derivative of u with respect, sorry, derivative of this total function with respect to x will gives me u v yx minus ux vy. You just observe that ux vy is cancelled out. So we will left with v uxy minus u v yx, which is exactly the same function which we have here. So that means this quantity is equal to v ux y minus u v yx. So that is we have here this quantity minus u v x y. Okay. So we'll note these things is there. The second one, that is a u v x. We'll start with this minus u a v x, where you just see that u, a, and v, all the three functions, they are the functions of x and y. So if I use the product rule here, by applying the product rule for three functions, the function a as it is, the function v as it is, a derivative of u, it is ux, plus function a as it is, function u as it is, and the derivative of v is vx, plus ax v u, that is u and v as it is, a derivative of v, sorry, a is ax, minus u, here we'll say it is ax v plus a vx. So if you simplify this quantity, we'll have it is a v ux plus a vx u plus ax v u minus u. We'll write down in the manner as we have written here. It is ax vu. So that is this, multiply this u with this two function minus a vxu. So just observe that this two quantity a vxu is cancelled with this, and ax vu is cancelled with this one. So the left quantity is a v ux. So what we have here, it is a v u, a partial derivative of this, minus u a vx. So this is the second things we got. Now the third one, similarly, now this calculation I'm not showing you, you just do it yourself. We have, it is b v u y is equal to b v u y minus u b v y. This is also the things we got. So you can start with this side, you will achieve this one as the way which we have did it here. Now, to see this one now, using this concept, what we have is VL of U. The notation for L of U is this. Minus U into I'm taking something that is Vxy minus A Vx minus B Vy plus Cv. So I'm just taking these two things. What is the simplification of this thing will gives me? Let us see that. What is AU? We already have AU. We have defined. AU is this. That is UXY AU B into Y plus C into U. Okay, so let us substitute that value here. So, and it will multiply with V. So we have it as V into UXY plus A into UXV plus B into UXY V plus CUV. And here it is of minus sign. UVXY minus minus become plus UAVX plus UBVY minus CUV. You just observe that the CUV will get cancelled out. And here we'll use this minus this is the concept we have written, that is VUXY minus UVXY is this quantity. So that we can substitute the value. So that means what we have it is VL of U minus VXY minus AVX minus BVY plus CV is equal to what we get, this minus this, that is VUY minus UVX XY, which due to this one we can write down this quantity. So that's why it is VUXY minus UVYX. That is this two quantity we have. Now here in this, that is AUXV. So that is AVUX, that is this quantity, is this much, which we have obtained here. So if I substitute this quantity as that, and the another one is, we'll use this quantity from here, that is BVUI is this. So we'll substitute this quantity and this quantity from the above expression. So it is plus AVUX minus UAVX plus BVUY minus UBVY. Now this quantity, this one is there already. UAVX of X, sorry, AV of X, it is X is outside. So it is AV at X. And this is BVY. So we have this U AVX which is of plus sign, and u bvy. So this is there, this two quantities cancel out. So we have this. Now just observe what we have here. Is this u a v x is cancel out with this one, and u b y is cancelled with this one, because this is of negative sign, this is of positive sign. So what is the quantity left? We're left with this quantity. We'll write this one as first, that is a v u x minus a v y x plus this quantity, this two, that is b u v y plus v u x y. This quantity will write down as a v u minus u v y at x, plus this quantity will write down as b u v plus v u x at y. So what we can have here from this, we can have, that is v l of u minus u m of v is equal to ux plus vx, where this m of v we have denoted. That means this quantity which we have here, that we have denoted as m of, here I have missed u, because previously I think so there is a u is here. So that is u into m of this. So that is m of v is vxy minus a vx minus b vy plus cv. That is from this. This function that we have here, we denote as capital U. That is capital U of x. So u is auv minus uvy that we have here. And this function, this one, will denote it as b. So that's why v equal to buv minus vux. Now this, if you can represent your operator L into this form as M, then this M, it's called the adjoint operator of L. The operator M, it's called adjoint operator of L. And if M is equal to L, it's called the self-adjoint. So this is the note we can write. If M equal to L, then L, it's called self-adjoint operator. So this is the definition of self-adjoint operator. Now using this operator, we'll use that one to discuss the solution of the wave equation, this concept. Okay. So for that, I need to have one theorem, which is known as a Green's theorem. The Green's theorem probably you have learned in your undergraduate course. into the advanced calculus, you have learned this theorem that is known as a Green's theorem, which having the relation between the surface integral and a line integral. Okay, so that is the relation between these two. So let us recall what is that theorem is. Let C be a closed curve bounding the region of intersect integration D, and U and V be differentiable function in D and continuous on C. Then we'll say that Green's theorem, by Green's theorem, it says that double integration of D ux plus vy dx dy is equal to integration, line integration of this u dy minus v dx. This is a Green's theorem we have already discussed into the undergraduate course, which having the relation between the line integral and the surface integral. So what is the surface D is there? This is the C, and the boundary is the C of D. So that is this entire things inside and as well as union this is the D, and is a region where U and V are the differentiable function defined on this D, and they are continuous on the boundary. Then we have this result. Now let us refer the Cauchy problem, which we already discussed earlier. The Cauchy problem is to find out the solution of differential equation by giving some curves depending on this. So the Cauchy problem is actually states like this. If you have so I'm talking about the Cauchy problem. We already discussed the Cauchy problem earlier also when we are dealing with the wave equation and the other equations. So we have a uxx plus b uxy plus c uyy is equal to capital F of xyz u ux and uy, where a, b and c are functions of x and y, and gamma 0 be the curve in xy plane. Then the problem of finding the u of xy or solution of uxy of this partial differential equation in the neighborhood of gamma 0, that is known as a Cauchy problem. So the problem of finding the solution of u of xy of the PDE 1, I will say 2. So PDE 2 in the neighborhood of gamma 0, satisfying certain condition, satisfying the condition u is equal to some constant f of x, some curve, or del u by del x, that is either velocity is given as some function, let's say g of x, certain things. On gamma 0, this value is there. It's called the Cauchy problem. And the conditions which we have stated here, these two conditions are known as Cauchy's condition. So here, to refer to this Cauchy problem, we are looking for a solution for certain equations as a Cauchy problem. So we'll start with this concept, and let us take gamma be a smooth curve. And we assume that the tangent to this gamma is nowhere parallel to x-axis and y-axis. We also assume that the tangent to this gamma is nowhere parallel to the x-axis or y-axis. So it is not parallel to this. Why? Because we have given the condition is x is constant and y is constant as a characteristic solution of the equation 1. So we already mentioned that this equation which we have in front of us, then this is a hyperbolic type and it has a characteristic as x is constant and y is constant. So that's why the solution, or we assume this gamma is not having no tangent is parallel to this x-axis and y-axis. We suppose that u and ux or ui, whatever the situation is there, are prescribed along gamma. That means the value of either u or ux or ui as per this Cauchy problem is defined on gamma. Now what is our objective? Our objective is to find out the solution of the equation 1 which we have talked in the neighbor of gamma. That is known as the Cauchy problem. Is exactly that I have stated here. So our objective, we want to find the solution of equation 1 in the neighborhood of gamma. That is will do. So for that, let us assume that P of alpha beta is the solution of such problem, Cauchy problem. So let P of alpha beta be a point at which the solution to the Cauchy problem is solved. Let the characteristics through P intersect the initial curve gamma at Q and R. That means let us see what is the figure we have. So let us consider this is your x-axis. This will be your x-axis and this will be your y-axis. Let us consider this is your curve, initial curve gamma. Make sure that your gamma is not having any tangent which are parallel to x-axis and y-axis. What we are assuming this characteristics through this P at this point. So we have a point P of alpha beta is passing through, that is at point Q and at point P here. So this will be the R and this will be Q. So that we have assumed that point P is intersecting the initial curve at R and Q. This is your x-axis and this will be your y-axis. Now we'll define now this region D, because I want to apply the Green's theorem which we have learned here. So let D be the region bounded by the closed contour of PQRP. Let us say entire curve is C. That means I'm taking this PQ, then this through this one, and this entire curve which we have denoted with yellow and green lines, green curve, is we call it as C curve. Now we'll apply this Green's theorem to this region. So we shall now apply Green's theorem to this region on using identity, that is this we have talked, this identity. We'll call it this is as equation number 3. So using this identity, what we can write? So here it is ux, uy. Here it's my mistake. This has to be y. Okay, so here it is ux plus uy is there. So that double integration of this quantity is actually a double integration of this one. So we'll use that one. Using the identity 3, we obtain what we got is double integration over d ux plus vy dx dy. As per the 3, we can say this is equal to double integration of over d vl u minus umv dx dy, and using the Green's theorem. What is the Green's theorem? Tells you that this double integration will change to single integration. That is this single integration u dv minus v dx over entire curve C. So that is equal to integration over C u dy minus v dx. So we'll have this using the Green's theorem. So therefore, finally what we can have is double integration over d VLU minus ULV dx dy is equal to integration over C. Now C will split into three parts because this curve is split into three parts. One through Q to R, that is through this curve, then it is R to P, and then it is P to Q. But here the direction is positive. Here it is direction is positive, and here it is in reverse direction. So we'll take in this direction and we'll apply onto the C. But since this is direction is reverse, we'll take it as negative sign. So that's why this entire curve is split into three parts, that is Q to R, U dy minus V dx plus R to P, U dy minus V dx plus P to Q, U dy minus V dx. And now what will happen to this dy dx? See, through P and P, R to P, if you can go through this is my y-axis is there. So y is constant here. Y is constant. Since y is constant, dy is 0. Here we have x is constant on this. So my dx is 0. So due to this, on the curve PR, on the line PR or RP, if I go in that manner, this will change to integration from Q to R. The first quantity is as it is, U dy minus V dx, that is on the curve. This will gives me plus R to P. Since your dx is constant, that is 0, so we'll have U dy minus P dq. Since this is, so dy is 0, so we'll have it is V dx. So that's why we have this. Now let us compute the last term of this, that is this quantity. Let us compute this. Now, integration from P to Q, V dx. Now, what is the value of V we have? Let us recall that. The value of V which we have obtained it from here, it is this. B UV plus, it has to be plus here. You just see that here it is plus. So that was my mistake. Here it is plus V UX. So using this, what we can say? This is quantities P to Q, B UV dx plus V UX dx. Now here the first quantity I will stay as it is, will write as it is. In the second quantity, we'll use the integration by parts. In this quantity, we'll use the integration by parts. So first one is as it is. Here we'll use integration by parts. By taking v as it is, a derivative of, sorry, integration of ux with respect to x will gives me u. A limit is from P to Q. That is minus integration from P to Q. A derivative of Vx, or sorry, V, that is Vx. Integration of u, that is integration of ux with respect to x is u. The whole integration dx. So this will gives me u into v p q minus integration from P to Q. If you combine this one and this one, we just see that u is common out from this two quantity. You will have u into dv minus vx dx. So this is the things we got. Let us substitute this value into this equation. We'll call it, this is equation number 4. So putting this value into the equation 4, putting this value in equation 4, we get integration from P to Q. Sorry. What we get is double integration over D ULU minus, sorry, ULV minus UMV. No, not this. Let us see. Is VLU minus U. This is MV. So it is VLU minus UMV dx dy is equal to integration from Q to R U dy minus V dx as it is, plus integration from R to PU dy as it is, and the value of this one will substitute. That is minus PV from PQ R. Then it is minus minus become plus because it is of negative sign. Integration from P to Q, U of U into BV minus VX, BV minus Vx dx. Now let us substitute the value of U here, value of U here, that is from R to P. So that can be rewrite as, so this is the quantity we'll rewrite as when I substitute the value, that is UV at Q minus UV at P. But this UV at P is of negative sign, positive sign. So that quantity I'll take on the this side, and rest of the all quantity will shift on to other side. So the first quantity we'll have it is UV at Q. That is this, which is of negative sign, which goes on the other side, will have a positive. Plus we have this quantity which is already there on this side. So that is double integration over D VLU minus UMV dx dy. This will already there. Now this quantity which is of negative sign, this is also, if I go take that quantity on the other side, then this is of negative minus Q to R U dy minus V dx. That is also there. This quantity will go on the other side, will have a negative sign. So since it is a negative sign, I will change that integration from P to R. So that's why it will become plus. Now it is P to R. It is R to P. Goes on the other side, it will have negative sign. So we'll change the sign by interchanging their limits. And the value of U is U into A V minus Vy dy. This is the value of U we get. And this final term, which is of again negative sign, So plus integration from p to q u vv minus vx dx. So finally we'll have this. This is the quantity we have. Okay, so this integration is required for further simplification. Now let us possible choose a function. So what we are doing is we're choosing the function v of xy alpha beta to be the solution of adjoint operator m of v equal to 0. So we'll find out sum of the function v is a solution of this equation, satisfying the condition vx is equal to bv on y is equal to beta, vy is equal to av on x is equal to alpha, v equal to 1 at x is equal to alpha, and y equal to beta. So this will satisfy this solution of m will satisfy this. And we just note here very important concept, this sum function v, it is called the Riemann function. Such function v, which is of function of xy alpha beta, it's called a Riemann function. So that is the definition of a Riemann function. Actually, the Riemann function is the solution of hyperbolic equation where the data is prescribed on the both the characteristic passing through the point P of alpha beta. If you know this information, then you can able to solve such thing. Now, since L of u is equal to f, which we have, we obtain from this integration, and at P, see P is the point where we have alpha beta. Okay. So at this point, due to this situation, now v, the value of v is at point alpha beta, it has value 1. So at P, it has value 1. So that's why it is u of at P is there is equal to v uv at Q, which we already have here. Now to this PR at PR, the value at PR, that is, we have a curve like this. This is the situation we have. This is our point P, that is alpha beta. At this point, the value of V is 1. Y is, this is the value R, and this is the value Q. So on Y equal to beta, that means this line. This is the line where Y is beta. Sorry, X is beta here. And this is the line where X is alpha here and Y is beta here. So on this line, Y is beta. So, and this line, the value of Vx, when Y is beta, that means at the QP or PQ line, the value of Vx is BV. So here PQ, the value of Vx is BV. Since it is BV, this quantity will be 0. Here, so this will tends to 0 due to this condition. X is equal to alpha, that is on this, that is the curve PR. The value of Vy is AV. Vy, the value of this one is AV. So that is also 0. So this is also 0. By taking this conditions, we can have this. And so what we get? This integration. Only this term is 0, this term is 0, these two terms will be left. Here the value of Lu, we already have it is, we already have MV is 0. That is MV is 0. Since MV is 0, this quantity will become 0. The left is VLU, but the value of Lu we have considered as F. So that means it will have plus double integration over D Vf dx dy. That is the quantity we'll have. Plus the integration for these things is left, that is q to r v dy minus v dx. Let us have that, that is plus, sorry, it is of minus sign, minus q to r u dy minus v dx. So this is the quantity we have here, that you can see. This is 0, this is 0, this is there. So we have this. That things is left is this. Now what is the value of u? Let us substitute that here. Let us recall what is the value of u we have. The value of u is AUV minus UVy. And what is the value of v? It is ABV minus, sorry, plus VUX. So this is the value of u and v we have. We substitute that value here. This will be UV at Q minus U dy. So it is AUV Q to R AUV dy minus U dy at y, means dy. What is the value of v? V is this. So plus, sorry, minus integration from q to r, because of minus minus become plus, so it will become plus BUV plus VUX dx plus this double integration over d v into f dx dy is there. Now we'll combine this term, this one and this one. We'll combine them, and the rest two things, that is this and this, will combine. So that's why we can have u at p is equal to uv at q. We'll have minus q to r. You just observe that uv is common from this two, so that's why it is, will gives me a dy minus b dx, because it is of negative sign. So that is a negative of uv is common out, a dy minus b dx plus q to r, the rest of the things, that is this u, that is minus minus plus, so u dy dy, so u dy vy dy plus v ux dx plus that double integration over d vf dx dy as it is. We call it this as equation number 5. Now equation 5 gives a u at p, value of the function u at p, when u and ux are prescribed along the curve gamma. When u and ux, if you can know, then you can able to find out the value of u at p. And this quantity and the identity PV at R minus PV at Q, that is equal to integration from Q to R UV at X dx plus UV Y dy. Why we get this? By applying just integration from P to Q, we'll have Q to R, we'll have this side, and that is exactly the same thing we have. If I use this one and gives along the same calculation along with the equation 5, that is u at p, we'll substitute this value of uv at q here. That means uv at q is uv at r minus this quantity. So we'll substitute that value from here. So that's why this gives me is equal to uv at r minus this quantity that is minus q to r uv at x dx plus uv at y dy plus this things is already there, that is uv at this value is already there, minus q to r uv a dy minus v dx plus q to r u d y dy plus v dx dx plus double integration over d vf dx dy. So we'll have this. Now we'll add, this is the equation number 6, we'll say. This entire equation is a 6. If I add this 5 and 6, the equation number 5 and 6, then that will leads to u at p. So what we are doing is adding 5 and 6. We get u at p. It is actually 2 times u at p, but that 2 is will divide here. uv at q plus uv at r minus 1 by minus q to r uv at a dy minus b dx minus 1 by 2 q to r u vx dx minus vy dy plus 1 by 2 q to r v ux dx minus uy dy plus double integration over vf dx dy. And this is the solution of that equation at point P of alpha beta, depending on Cauchy's problem, depends on this, the curve QR. That means QR is on gamma, which we have. So this is the solution which we got, which will be depends on the curve gamma. And that is the Riemann method that we have. We'll discuss certain examples of Riemann methods in the next lecture. Okay. So if you have any questions, you can ask.